Welcome to this Chemspeed webinar, the fifth in our series about digitalization in R&D and QC labs. I'm Amira Abu Hamdan. I'm a chemist, first and foremost, and the Vice President of the Materials Science Business Unit with Chemspeed Technologies. And I will be your host today. In our webinar series dedicated to the digitalization of R&D and QC labs, we strive to offer this platform to our Chemspeed partners and solutions users to share with you directly, firsthand, their experiences and ways to success. So in the course of the coming months, they will regularly describe how they make use of our automated solutions, how it relates to digitalization, and what it means for their current and future operations. Today, we honor the over 10 years of collaboration between Chemspeed and Professor Andy Cooper at the University of Liverpool. It is my pleasure to introduce Professor Andy Cooper, a renowned professor and the founding director of the prestigious Materials Innovation Factory at the University of Liverpool, as well as the academic director for the Leverhulme Research Center for Functional Materials Design. Professor Andy Cooper is a graduate from the University Nottingham, where he obtained his PhD for the study of organometallic reaction mechanisms at low temperatures and high pressures with Professor Martin Polyakov, and he has gone to hold a number of prestigious fellowships, including an 1851 fellowship and a Royal Society NATO fellowship at the University of North Carolina, working with Professor Joseph De Simone. He has also held a Ramsey Memorial Research Fellowship at the Melville Laboratory for Polymer Synthesis in Cambridge, working with Professor Andrew Holmes. In 1998, Andy was awarded a Royal Society University Research Fellowship and joined the University of Liverpool in January 1999, where he now holds a personal chair. Andy, thank you very much for joining us today. We are very excited to witness through your presentation how the work of a chemist has already fundamentally evolved, making use of digitalization tools, automated solutions, predictive modeling, and AI. And of course, we are happy that you had opted for the use of the Chemspeed enabling solutions. This is the way we will run the webinar today. During the next half hour, Andy will share with us his presentation entitled Digital Design and Discovery of Functional Materials, and we will then have time to answer questions. In fact, you can type your questions at any time in the Q&A section on the right-hand side of the screen. We will strive to answer as many as possible, and we will get back to you by email with the unanswered ones. Now, I hand over to you, Andy.
Okay, thank you, Amira. Nice to be here today to speak in this webinar series. So I'll talk to you about our work in the digital design and discovery of functional materials. And I'll focus on automation platforms, but not only automation platforms, also some of the computational work we're doing alongside these platforms. So we work on materials, and we're interested in what you might call digital design of materials. So that is designing materials in a computer. And we're also interested in the experimental discovery of materials. And I'll give a couple of examples here, not from my group, but from other groups, and MOFs that were designed by Professor Edwardi, and some perovskites which were discovered using automation technologies in groups of Schreier, Norquist, Chan, and others work, much of it done in Berkeley. So these, are, to some extent, are two different approaches in silico design and experimental discovery, but as I'll show you, I hope we're trying to increasingly join them together. So It would be great if we could design all materials in a computer, then we wouldn't even need a lab, let alone a robot. You could just design things and then someone could make them. And that's not yet possible, but in some cases it is possible. And we've been working in this area for about 10 years. A lot of this work in collaboration with my colleague Graham Day at the University of Southampton in the UK. So the idea here is to design materials in a computer without having to do any lab experiments. And this gives an example, which I don't have time to go into the details, but where we predicted 5 different forms of a material, all of which exist in the lab and can be predicted as being stable from these energy function maps, energy structure function maps, where effectively we're calculating the stability of the material to determine whether it's likely to exist in the lab. And here we find 5 different forms of this molecule T2, and they could all be made in the lab. And if you look at the agreement between the predicted crystal structures in red and the experimental structures in blue, you get an almost perfect agreement. So we predict that these materials will exist, they do, and they exist exactly as predicted. You can also predict the properties. This is the methane storage capacity, which is relevant to gas-powered vehicles and other technologies. And without going into the details, these maps show that one of the molecules, this molecule, is more promising for methane storage. And then when we did experiments in the lab, that was shown to be true. So this is what you would call in silico design. But a lot of properties can't yet be fully predicted in silico, so we still need to do experiments. But these are important approaches, I think, because they give you a map, like a treasure map, to tell you where to look. But I should say, even with these computational predictions, and I'll show you in a few slides, you still might have a very large experimental space to explore. So the predictions might tell you to look at molecule X instead of molecule Y, but it doesn't actually tell you how to make that material or where to, or what solvent to use or what conditions to use. So we still rely very heavily on experiment, and that's where automation becomes very enabling. And I'll give some examples of Chemspeed automation. So I'll talk a little here about porous organic cages. So these are molecules that have a cavity in them and a hole in them. And these molecules can do interesting things, such as separate xenon. So this is a molecular dynamics simulation showing xenon hopping through the cages. And because the xenon is retained in these cages, because it's a very good fit, then it can be separated from other gases. And we got interested in making these molecules, and we wanted to increase the synthetic diversity of these molecules to make a larger number of types of cages. But there are very many building blocks, and this gives just a small, relatively small number of possible building blocks. But even with this library of amines and aldehydes, there are several hundred possible combinations, and you can quite easily think of thousands of combinations. So we used the Chemspeed synthesis platform here, which we have in our labs, to explore this space rapidly. So taking libraries of amine and aldehyde building blocks and putting them together. And I should say this work was done, led by Rebecca Greenaway, who is now at Imperial College, and Kim Jelfs did the predictions. She was and still is at Imperial College. And I don't have the time to go through the detail here, but what we found is the results that we got in the lab in terms of the cages which were formed and the cages which were not formed agreed really very well with Kim's simulations. So we actually ran all of these reactions, and we could do that because the Chemspeed allows you to do reactions very quickly. But actually, we could have used a smaller selection. So the one shown in red didn't work. And actually, to some extent, that was predicted by Kim's simulations. So we could have used a smaller number of amines and avoided these red areas. So this is an example of combining computers and automation systems in a way that you still have to do a lot of experiments, but you can filter the number of experiments using predictive simulations to avoid bad areas. So then it's not simply combinatorial screening, it's digitally guided searching. And just to give you a sort of indication of the number of structures we made, these are the cages that we made, some of the new cages that we made. And there's a wide diversity of sizes, shapes, cavity, geometries. So there's quite a lot of diversity in this library that was made on the Chemspeed platform. And just to give you an idea of how fast this is, so we've been working with organic cages since 2008 or so. And this graph shows the number of new cages that my group, not the whole world, but my group reported in the literature over about 10 years. And you can see that this one study on the Chemspeed platform, we formed actually more new cages than we had formed in the whole of the decade before that. So this really is enabling, and using this Chemspeed synthesizer, we actually produced more new molecules than we had produced hitherto. And we didn't just produce more stuff, we also found some totally new things. So this is a very interesting molecular geometry. It's a unique geometry, had never been seen before, and it's a doubly bridged, triply interlocked cage catenane. So it combines covalent bonding and mechanical, so-called mechanical bonding. And that topology had never been seen, and only two of the combinations gave this particular topology. So if we had looked at a smaller number of combinations, we surely would have missed this. This was a function of looking very broadly. And it shows that, you know, robots in labs can not only speed up discovery, but also find new things. So we wanted to kind of show that point rather specifically, because sometimes people are skeptical about new things using robots in labs, and did you really find it, or did you perhaps know anyway that it existed? So we deliberately went back to a very old molecule, trimesic acid. The first crystal structure was reported before I was born, and this was in the days when molecular models were plastic models hanging on fishing wire. So this molecule's been studied for, when we started this work, had been studied for 50 years. And we deliberately chose it on the basis that there might not be anything new to find out about trimesic acid, because it's been studied. There are hundreds of papers. So we chose it specifically for that reason, to prove the point that you can find new things. And sure enough, if you do crystal structure prediction, and this is the lattice energy plotted against the density, we predict some new forms of this molecule, some new polymorphs, form 1 and form 2, and they emerge as spikes on the energy landscape. That means they are unusually stable at the given density. So we did, actually Graham Day's group in Southampton did these predictions, and immediately looks like, well, there are two forms here that look interesting. They look like they should be porous, and they weren't in the literature. So even for this old molecule, we get a suggestion that new things might be discoverable. But the problem is, obviously, if these polymorphs were easy to make, then they would have been made in the last 50 years. So what these predictions don't tell you is what conditions you need to use to access these polymorphs. So what we did is, again, use the Chemspeed platform, slightly different setup, but to do crystallization. And basically, we dissolve the molecules in various solvents. The Chemspeed then forms different solvent combinations, and we can screen a very large number of solvents for crystallization. Then we get a large number of powders from the crystallization. We transfer those. At the moment, we do that bit manually into a powder diffractometer plate, and then you get a set of powder X-ray diffraction patterns. And you can compare those powder patterns with the predicted patterns from the simulations. Here are just a few of the patterns. You can see, obviously, we're getting lots of different structures here because there are lots of different patterns. But so we have maybe 10 or 20,000 predicted structures. We have 280 structures from the experiment. So it's a 280 times 20,000 array. It's quite a big job to compare all of this data, but you can do it. And then, long story short, we find that this spike here, this is the similarity colored in red. We find an almost exact match. So this predicted form, which is at the bottom of this spike, this is the experimental structure. You can see it matches exactly. So we found this predicted form that was suggested by the simulations. And why is the robot important? Why is the Chemspeed important? Well, it actually only forms under 2% of the conditions that we studied. So only 6 crystallizations out of 280 gives this form. And that explains why it wasn't found in the last 50 years. It actually only forms under very specific conditions. And it's fair to say that we never would have looked without the predictions, because trimesic acid is an old molecule. There wouldn't have been any reason to do 280 crystallizations. So this is another example of coupling simulations with automation. So the simulations tell you what to look for, and then the Chemspeed makes the crystals, and then we find the thing that was predicted. So there are 2 examples of joining digital prediction techniques with Chemspeed automation. And you can think of lots of other contexts where that might work, in drug polymorph discovery, in agrochemicals, and lots of other areas, I think. But there are still some challenges. And one of the challenges is in materials chemistry, there's a very wide variety of forms, such as solids, pastes, and liquids. And actually, the Chemspeed hardware, different forms of the Chemspeed hardware can handle all of these different types of materials, solids, liquids, and pastes. But a bigger, perhaps broader issue is integrating a very wide variety of instruments. So in materials chemistry, there's a very wide diversity of instruments which are used. And some of them are just physically big. So an X-ray diffractometer and high-field NMR, these are very large instruments. And some are very expensive. So squid magnetometry is a technique that's expensive. Single crystal X-ray diffraction is very expensive, maybe costs £500,000 or more. So there's the question of how to integrate these instruments into automated workflows. If the instrument's small, such as gas chromatography, then it's relatively straightforward. But if the instrument's very big, or perhaps in a different room, then that can be challenging. So we created this new approach in the last few years, which is using mobile robots to couple together different operations. So by having a mobile robot which works in a lab, it can integrate instruments in principle wherever they are, even if they're in separate labs or even in different buildings, because now you're automating the chemist rather than the instrument. So this is the robot that we used, the first robot that we used, and it's made by a company called KUKA. And it moves around the lab. More commonly has been used in manufacturing rather than a lab setting. But what it does is it maps the lab using a laser, and it can navigate the lab. And you can monitor this remotely. So this is Benjamin Berger, the student who did this work, and he's monitoring the progress of the robot from his flat. So this is quite useful in times of social distancing and COVID, for example. You can monitor and control the system remotely using cameras. And this system can do a variety of things. It can do solid dispensing, it can do liquid dispensing. can do reactions. This is a photochemical reaction block, and it can do measurements. In this case, it's chromatography. But what it does is not only does it work, you can work remotely, it can also work autonomously. So the system can do experiments by itself using artificial intelligence. So I'll show you a video of this in operation. So the robot's doing solid and liquid dispensing, capping, measurements. The reaction is happening here in this photolysis station. And it's completely autonomous. So there's no human input. The robot's actually making the decision about what to do next using an algorithm. So it's fully autonomous. And in this video, which runs for about 60 seconds, it works for 48 hours without stopping. And it measures about 100 samples a day. And for comparison, before we built this, when we were doing it manually, we could measure 1 or 2 samples a day. But I should say it makes the samples and does the reaction and does the measurement in a loop. So the way that works is, and I won't go into the chemistry here, but this is a catalysis experiment. There are 11 components, and when you work it out, there are something like close to 100 million possible combinations. And what the algorithm does is it starts with random conditions initially, and then it applies an optimization process called Bayesian optimization to find more effective catalysts. This is the catalyst activity. So in practice, you simply need to load the system with the solids and the liquids that you're using in the search, and then press run, and the robot and the algorithm does everything else. So this animation shows the data as it comes off the platform. This is a experiment that ran over 8 days. And you can see this, the catalyst activity starts quite low because the initial conditions are random. But then very quickly, as you do more experiments, the catalyst activity gets better. The algorithm finds better combinations. And after about 650 experiments or so and 8 days, we've gone from an activity of about 3 in these units to an activity of more than 20. So we've got something like a six-fold increase in the catalyst activity without any input from a human. So it's completely autonomous optimization. And in principle, you can do that with anything that you can measure. In this case, it's catalyst activity, but it could be reaction selectivity or enantiomeric excess, or maybe some biological activity for a drug or something else. And this gives some statistics. Over this 8-day period, the thing travels about 2 kilometers around the lab, and it works for 172 hours. The reason it's not 192 is it has to charge its battery for some period, so it works for about 22 hours a day. And we're looking at some other technologies. It's not only limited to these particular mobile robots. There are other types of robots that might be useful in this context. This is a 2-armed robot made by ABB that can remove caps from vials. And you can begin to string these things together, where in this case, one robot passes the vial to this robot, which removes the cap. So you can imagine these things working in teams and having mixtures of static and mobile robots. And it's also, in principle, compatible with Chemspeed solutions. So here, this is an early stage implementation. We're still working on this, but it's definitely feasible to imagine these sorts of robots delivering materials to a Chemspeed reactor station. Or this is actually a Formax Chemspeed system that's more designed for formulations. So you could imagine a system like this delivering reagents or formulation components to these sorts of platforms. effectively fulfilling the kind of technician role of loading up reactors. The difference being that it can do it 24/7, do it, and if the reagents run out at 3 a.m., then the robot's not sleeping. It's not in a nightclub. It can deliver things on demand at any time. So I hope I've shown you that we can do both simulations and also discovery using Chemspeed automation. I think these new platforms, mobile platforms, offer a link between these two types of approaches, where you can imagine using this kind of mobile technology to put together much more complex workflows and to integrate equipment and techniques that would otherwise be really difficult or challenging to integrate. So we think these things can work happily in a combined workflows, and really our dream and what we're trying to do in the next 5 years is to string all of these things together. So we have truly autonomous experiments where the design happens in silico, and then some steps are done perhaps using these types of systems, and some steps are done using Chemspeed systems. And we put this stuff together, you have a discovery process which is quite different from anything that exists today. That's our goal. So with that, I'd like to finish. I'd like to thank Chemspeed. I've actually worked with, I'm trying to remember when we bought our first Chemspeed system. I think it was about 15 years ago, actually. And we're looking at a new system now. So we've used that hardware for a long time. It's been very successful, and it's led to a lot of great breakthroughs. So, and thank you to Chemspeed for their continued support and help with that. And with that, I will finish, and thank you all for your attention.
Thank you very much. Thank you very much, Andy, for your inspiring presentation and sharing with us all the breakthroughs. I believe that it's definitely clear how the way chemists work has already fundamentally changed. I am very curious now to move to the questions from our audience. And here's the first question. So getting energy landscape versus density for all possible conformation is combinatorial. Could you comment on your parameter search, e.g. the Bayesian optimization or annealing approach? And
yeah, if I follow the question, certainly the energy landscape, the ESF map approach is combinatorial, and you're searching an enormous space, and usually we have to apply some constraints. So sometimes we approximate the molecules as being rigid, for example, and we typically only allow for one molecule per unit cell in the structure. Otherwise, the space simply gets too large. So it is true to say that some crystal structures are still just too complex to address with crystal structure prediction. The Bayesian optimization, that was more about so we use annealing approaches in the crystal structure prediction. The Bayesian optimization was more about the robotics and the experiment search, though it is possible actually to apply Bayesian optimization to energy landscapes as well. So that's also possible. I hope that answers the question.
Thank you, Andy. Can we have the next question, please? Filtration is a tedious step. How is this done in your case?
That's an interesting question. I mean, I don't know why I pick on filtration. I guess weighing is a tedious step as well, you know. So, but yeah. So the workflow that I showed in the video or the videos, that there's no filtration in those steps, in those processes. But for the Chemspeed experiments. There are some sort of established ways to do filtration on Chemspeeds, either using Fritz and transferring from one reactor into another, or other methods. So yeah, we can and we do automate filtration on Chemspeed platforms. That's the answer. We use a Chemspeed.
Thank you. Can we have the next question, please? Okay, very cool. So what software do you use for the design process? Can you talk more about the in silico methods? Thank you.
Yeah, the answer is it depends. Some of the work that I talked about with the Chemspeeds was done using classical factorial design, so combinatorial factorial multivariate design, and that works quite well for some things. Depends how big the search space is. For the mobile robot search, it was done using Bayesian optimization, so that's slightly different. You start with effectively random conditions and then optimize using a batched algorithm. So there are lots of approaches to experimental design, ranging from classical combinatorial design to Bayesian optimization, reinforcement learning. I think the answer is it depends how closed loop your process is. So if you're going to make a batch of 200 polymers, then you might use combinatorial factorial design. If you're going to do closed loop optimization, then it's probably better to use an algorithm. So the answer, I think, is it depends on the problem and it depends on the automation that you're using.
Okay, thank you. Can we have the next question, please? Have you ever tried to use a software to predict novel chemistry routes and tried it out on the Chemspeed platform?
No, we haven't done that. So we haven't done any sort of retrosynthetic predictions of that type. But I'm not the right person to ask about this, but there are examples. I have a feeling this was something that was discussed in the IBM Chemspeed webinar, but we haven't done that ourselves, no. But I refer the questioner to other people there.
Mm-hmm. Okay, can we have the, thank you, and can we have the next question, please? So what parameters can be adjusted during a crystallization screen, such as the one presented on the trimesic acid, e.g. pressure, anti-solvent, temperature, etc.?
So yeah, we essentially did it using variation of the anti-solvent, and that was how we approached it in that case. You could also do it by varying temperature, and the Chemspeed decks you can do that. You can change the temperature. Haven't considered doing it by changing the pressure. In principle, that might be possible. We haven't done that. You could do it by obviously you can control the rate of solvent evaporation up to a point. But the main approaches we used have been varying the anti-solvent and in some cases varying the temperature. And that can already give you a very wide diversity of conditions. Mm-hmm. Often too many conditions, actually. The problem is often constraining it enough to be, manageable. So anti-solvent is the one we've had most success with.
Okay. Thank you. And can we have the next question, please? Crystal structure landscape. How did you calculate and what are the computational programs used?
Well, there are a few different ways to do that, but the work I showed here was done actually in the University of Southampton by my collaborator Graham Day, and he has a sort of bespoke approach that he's built himself. But basically, it uses parameterize force fields as the main computational approach. It is also possible to use density functional theory, but it gets very expensive for large, especially for large complex molecules. So we don't tend to do that, but some groups do. If you're a pharmaceutical company and you've got lots of money and lots of computers, then you can do DFT. There are a few different commercial software packages as well, but they mostly have some limitations. So the answer, it's slightly too complicated to answer in a simple way, but it's a set of methods developed by my collaborator Graham Day that actually have evolved over quite a number of years. Actually, the original code was written in the 1990s, but it's been built on over the last 25 years.
Okay, thank you, Andy. Next question, please. With your novel porous organic cages work, your group managed in months using automated solutions and predictive modeling, the equivalent of what was manually prepared in years. How much further added value do you project by integrating the robot chemist component?
Yeah, so we haven't done that yet. It's a good question. So when we did that work, I mean, it's highly automated. The Chemspeed, does all of the synthesis work. But ultimately, if you wanted to make it a lot more cages, then, you could imagine loading and unloading the Chemspeed using a mobile robot. So if instead of making, 100 cages, you wanted to make, 10,000, then there might be some value in having, really closed loop system. I mean, that said, then you might hit a different bottleneck, which would be maybe the characterization. But so the answer is we haven't done that yet, but that's the kind of thing we're beginning to look at. Is if you wanted to do long-term, experiments where you did 100 reactions, then another 100, then another 100, you could add value by reloading the Chemspeed with a mobile robot, for example.
Mm-hmm. Thank you. Can we have the next question, please? Studies of trimesic acid in the literature are well documented. If you didn't have access to Chemspeed automated platforms, would you still have had carried out the study manually? And what is the advantage of integrating more robotics? I think this is getting also close to the previous one a little.
I mean, the short answer is no. It's a 50-year-old molecule. It's easy to answer in hindsight. If 2% of the conditions give the result you're looking for, then I think the answer is no. We wouldn't have done it because it would have taken a huge amount of time with no guarantee of success. I mean, only 2% of the solvent conditions gave this interesting form. And if it was, the risk of spending a year looking for this thing, I suspect we wouldn't have done it. And I think that's the power of these platforms, is you can try risky things that you wouldn't otherwise do.
Mm-hmm. Okay. Thank you. And can we have the next question, please? How will this technology impact the chemical education and training? The future chemist will have less hard skills?
Yeah, I've been asked that question quite often, actually, is will it mean that, we have a generation of chemists that don't know how to do a titration or something? The answer is I don't think so, not least because I think it will take quite some time before this technology enters sort of just education, training. So I suspect for quite a long time, maybe forever, that these technologies will be used in research labs, not in university teaching labs, I suspect, for a while. So I think we'll still train chemists in the core skills. The other point I'd make is this is already happening. You know, I mean, I'm old enough that I did my PhD in spectroscopy with old instruments where you really did have to understand how they worked. You know, and I did my PhD in FTIR. But now FTIR, you just put the sample in and press run, and nobody knows how FTIR works. So I think to some extent it's already happening. It is a concern, but I don't think robotics is any more of a concern than any number of other technologies, you know. Like who knows how a PC works, but we all use them. I think the point is it frees up people to think about the chemistry. And I don't know if pipetting is a great hard skill, you know. People used to mouth pipettes, you know, which was really dangerous. So some of these things are probably better lost, actually.
Thank you, Andy. Next question, please. You have mentioned automation allows you to search larger chemical spaces faster. Are there any other areas of old chemistry that you think applying automation to would enable the discovery of missed opportunities?
Yeah, I mean, the trimesic acid example, it really was done just to make a point, to show that you could find new things about old molecules, but not for practical reason. But a more practical application might be to look for, you know, I don't know, pharmaceutical activity in molecules that aren't known to have pharmaceutical activity, for example. You know, I mean, it's quite possible that there are a lot of molecules in the chemical space which are pharmaceutically active, but they've never been studied in a pharmaceutical context. So there's one possible example, is to look for molecules that actually have drug-like activity, but nobody ever looked. And I could think of others, but that would be one.
Mm-hmm. Okay, thank you. Can we have the next question, please? So for the prediction structure, do you need crystal structure first?
No. The way the method works is you predict the structure of the molecule in isolation, if it isn't known, if it's a new molecule, for example, and then you predict from first principles. So you build candidate crystal structures, then you calculate the stability. So no, you don't. No, it's de novo. So you can do this for molecules that don't exist. You can do it for things that have never been synthesized. So no, you don't.
Okay. Okay, thank you, Andy. Do you have one? We can take one more question. Thank you very much for the valuable lecture. That's what I wanted to say. Would you kindly elaborate more on how your combined approaches can help towards the synthesis of functional nanomaterials, e.g. for energy storage?
Yeah, so I didn't really explain what the catalysis thing I presented was. It actually was photocatalytic water splitting. So it's not energy storage, but nanomaterials for energy production. I guess it depends what the questioner means by energy storage. There's no reason you couldn't use these automation approaches for battery research, for example. I mean, some of the operations in battery assembly are a little more sophisticated than liquid and solid handling, so it might be more challenging, but battery research could be possible. And there are some automation platforms that already address that. I think there's a lot of scope for doing research in flow batteries, which is an emerging area. I can certainly see how you might automate flow battery discovery, perhaps more easily than solid state batteries. So yeah, I think there's lots of potential there.
Okay, Thank you, Andy. That was our last question we can take for this session. And as promised, we will get back to you by email with the unanswered questions. So, Andy, thank you so much for having shared with us your vision and your intensive digitalization experiences that you rolled out in your research for many years now, with confirmed success and breakthroughs. And we look forward to learning about your next endeavors. Thank you. So I'm closing now. This was the 5th webinar in our series about digitalization in R&D and QC labs. For more information about our next events in this series, please visit our homepage. Thank you all for your attendance and your active participation in the Q&A too. Thank you.